for this first example, I would like everyone to try on their own. Given the two angles, classify each triangle by its angles and sides. And feel free to use your calculator for these questions as well. So for the first one, we have a 55-degree angle and a 43-degree angle. Okay. So if we have a 55 and a 43-degree angle, we have a 98 degrees in total. And so 180 minus 98 gives us 82. So the third angle is 82 degrees. So if you look at all of these angles, they're all acute angles. And since they're all different, this will be a scalene triangle. So acute, scalene. Now if we look at the next one, if we add 47 and 43, we get 90, making the third angle 90. And so this is a right scalene triangle, since none of the angles are the same. So for the third one, when you add 33 and 33, you get 66. So the third angle is 114 degrees. And so you know that 33 and 33, it's isosceles, but we also have this obtuse angle. So we have an obtuse isosceles triangle here. So make sure you're comfortable with identifying the type of triangles that we have, and make sure that you're studying these triangles as well. Okay, so the notes that we're going to take today are called angles of polygons, and we're going to look at interior and exterior angles of polygons. Okay. So the definition of a polygon is an enclosed figure made up of 3 or more sides. So we have our triangle is our first polygon, and then we can increase from there. But every polygon is either concave or convex. So we don't know the definitions of these terms yet, but if we recognize and look at the two diagrams below, I want you to draw these figures. Which one would you suppose is concave? Okay, and which one would be convex? So when you look at the word concave, is there a word that pops out at you? I mean, I see the word cave. So when I think of the word cave, I think cave in. So if you look at this yellow or the pink figure, notice how it's caving in and going inside of the figure. So you have a point that's inside of the figure. So here this is concave. And then this figure, notice how none of the points are inside. We'll call this convex. So the definitions of concave and convex are as follows. Okay. Convex is all interior angles are less than 180 degrees. Okay. So if we're looking at that, notice how we have, this would be convex. Okay, so with this one, convex. And if we think about a concave figure, one interior angle is more than 180 degrees. So if I look at this figure on the blue figure on the top left of the page, so we have a right angle here and a right angle there, and we have an acute angle here and an acute angle there. But we also have this other angle, which is this angle bigger than 180 degrees. So that's an interior angle, it's inside of the figure, and it's more than 180 degrees, so this is concave. And now if we look at the star, we have an acute angle, right? We have these acute angles all on the outside, but look at this angle, okay? That's more than 180 degrees. Look at this angle, more than 180 degrees. So this is also concave. And a circle. A circle is not a polygon, because a polygon is made up out of segments. There are no segments on a circle, right? There are no endpoints and no actual segments that we can measure since it is rounded. So we're going to look primarily at convex polygons as we go throughout this unit. what I want us to do is pause, and I want you to give me the proper names of these polygons. So for example, the first polygon is a triangle. Okay. And I want you to pause and fill in the rest. So we have a four-sided figure, which is a quadrilateral. Okay. And then we have a five-sided figure, a pentagon, six-sided figure, hexagon, seven-sided figure, heptagon, or can be a septagon. Okay, either one will work. Eight-sided figure is an octagon. Nine-sided figure, nonagon. And then we have a decagon. And if we have a figure with n sides, we'll call it an n-gon. Okay? So if something had 23 sides, we call it a 23-gon. All right, not too fancy. But recognize that we have this piece here. This is going to be helpful, this n-gon. We're going to be seeing quite a bit. Okay, so when we name polygons, we want to name them by the type of shape they are. So in this first figure on the left, we have a four-sided figure. It's a quadrilateral. So I can name it quadrilateral A, B, C, D. And what you do, you just simply name the points. But you have to go in order. Okay, and it doesn't have to be alphabetical. So I could say D, A, B, C. But we can't say DBCA because it's giving it out of context. So we have to read it left to right or right to left and make sure you're going clockwise or counterclockwise. And so for this next figure, we have 1, 2, 3, 4, 5, 6 sides. So it's a hexagon. And I'm going to start at P and then keep going. So P, Q, R, S, T, U is the name of that polygon. Okay, so you're just naming all the vertex points when you're naming them. All right, so in this diagram, I want you to draw each of these, and then we're going to describe each of the figures below. So for this first diagram, we don't know anything about the angles, right? The angles aren't marked as congruent, the sides aren't marked as congruent, but this is a 1, 2, 3, 4, 5, 6-sided figure, so this is a hexagon. And we'll call it an irregular hexagon because we don't have any sides congruent, we don't have any angles congruent in this picture. So for the next one, we can describe this. All of the angles are the same, so we can call it an equiangular hexagon. Okay. For this third figure, we don't know anything about the angles. We still know it's 6 sides, but we'll call it an equilateral hexagon. And then finally, for this last picture, notice how both the sides and the angles are all congruent. Okay, all the sides are congruent to each other, and all the angles are congruent to each other. So this is what we call a regular hexagon. Okay, where all the sides are congruent and all the angles are congruent, a regular hexagon. So a regular polygon in general is a polygon with congruent sides and angles. So it is an equilateral and equiangular figure. Okay, so if we look at a triangle, an equilateral triangle is a regular triangle. A square is a regular quadrilateral. Okay, so we need all the sides and all the angles congruent for it to be regular. And this is important as we're going to jump into the next bit. Okay, so we're going to use our knowledge of diagonals to help us find out how many degrees are in these types of polygons. So we need to know what a diagonal is. And if I put, you don't have to draw this, but you should write the definition of a diagonal. Okay, a segment joining non-consecutive vertices. So if I have this figure, if I put my pencil on one of the vertex points, I can draw a diagonal to that vertex point. I can also draw one here. I can draw one here, and I can draw one here. So a diagonal doesn't have to cut a picture in half, doesn't have to cut a polygon in half, but it's a segment joining non-consecutive vertices. So notice how these vertex points are left out because they are directly next to that initial starting point. So now we're going to look at triangles, quadrilaterals, pentagons, and we're going to see what we can come up with, see if we can find a pattern. But we know that the sum of the interior angles in a triangle is 180 degrees because of the triangle angle sum theorem, okay? And now, in looking at this second picture, a quadrilateral, does anyone know what the sum of the angles in a quadrilateral are? Okay. So some of us may remember this as 360 degrees. And so we're going to discover why that is by drawing a diagonal from one vertex. So when we draw this diagonal, we have two triangles that are created. We have 1, 2, these two triangles. So 180 times 2 gives us 360. Okay. So now for this pentagon, I'm going to start at this top point. Let's see how many triangles we can create. We could break this up into using our diagonals. And we have 3 triangles. So 180 times 3 gives us 540 degrees. So for 3 sides, it's 180. For 4 sides, we're adding 180 to that, or 360. And then we're adding another triangle for a 5-sided figure. And so we're seeing a pattern here. So I want everyone to create this chart in their notes. Okay, this will be helpful as we go through. But I can't draw any diagonals in a triangle, okay? But I know that the sum, there's one triangle that we have, and the sum of the angles is 180 degrees. We can draw one diagonal in a 4-sided figure, and 2 triangles are created, and that gives us 360 degrees. Okay, so we have 180 times 1, or 180 times 2. And then we can draw 2 diagonals, 3, 4. Notice how this is going up, right? And when we're looking at this, we see that the number of triangles also increases by 1. Okay? So I'm going to leave this last column blank because this is for a triangle with n sides, so when we don't know the number of sides. But if I'm looking at the number of sides in this column and the number of triangles, we can find the interior angle measure. So for a 5-sided figure, we had to do 180 times 3 of the triangles to then get 540. And for the next one, we had 180 times the 4 triangles, and we can use our calculator to then get 720. For a 7-sided figure, we have 5 triangles that we can create. So 180 times 5 gives us 900. And then we can do 180 times 6, which gives us 1080. 180 times 7, which gives us 1260. And then 180 times 8 gives us 1440. Okay. So now we're in our last column. Like, what if we don't know how many sides we have? Okay. But if we look at the number of triangles that we have, or the number of sides, and the number of triangles that we have created, let's see, we go from 3 to 1 triangle created. And then we go from 4 sides to 2 triangles created. And then we go from 5 sides to 3 triangles created. So what do you have to do to the number of sides to get the number of triangles you can create in that diagram? You have to subtract 2. And then to find the measure of the angles, we have to follow this formula. 180 times n minus 2. So this is a theorem, the interior angle sum theorem. So the sum of the measures of the interior angles of a convex polygon with n sides is 180 times n minus 2, right? And that's going to give us a degree measure. So now if we were looking at a regular pentagon, okay, a regular pentagon, that means all the sides are congruent and all of the angles are congruent, okay? So when we do 180 times 5 minus 2, right, we have 5 sides, we get 540 degrees, and that is the total sum of the angles. But I just want to find one angle in a regular pentagon. So we know that they're all the same, so we can divide by the number of sides. And then from there we can do 540 divided by 5 in our calculators to get 108 degrees would be each of these angles. So here's the formula for finding one interior angle for a regular polygon. So it must be regular to use this formula. Okay, so we're going to divide by the number of sides. So n is the number of sides still. Okay, so make sure you have the formula written down. All right, now we're going to talk about interior angles versus exterior angles. So if I'm looking at this first triangle, we have a 40 degree and a 60 degree, so that means this is 80 degrees. But if I draw in the exterior angles, okay, we have a 100 degree exterior angle, 120 degree exterior angle, and a 140 exterior angle. So when you add up all of those angles, 140, 120, 100, what do we get? We get 360 degrees. Let's look at this middle figure. So all of these exterior angles must be right angles, okay? Because an interior and an exterior angle are a linear pair. They add up to 180. So if I have 4 times 90, that also gives us 360 degrees. How about for this quadrilateral? So if I drew exterior angles, we have 100 on the top, and then we have 80 on the bottom. So if I add 180 plus 180, we get 360 degrees. So notice how for all 3 of these figures, the exterior angles will add up to 360 degrees. Okay, so we can do the same thing for these as well, right? Each angle would be 72 if all of these were the same. So 72 times 5, right? We have 5 exterior angles, so 72 times 5. That also gives us 360 degrees. And notice for this last one, every exterior angle would be 60. And so 60 times 6 is also 360. Okay, we could keep going. So, moral of the story, the sum of the exterior angles of a convex polygon always equals 360 degrees. So this is a fact that we should just know, okay? And so if you were finding the measure of one exterior angle of a regular polygon, we can say 360 divided by n, the number of sides, equals the exterior angle. So that's another formula that we can look at. So let's look at this example to finish out the notes. But if each exterior angle is 10 degrees, then how many sides does the polygon have? So each exterior angle is 10 degrees. So I'm going to plug into this formula. If my exterior angle is 10 degrees, then I can solve for n. And to solve for n, I'm going to multiply both sides by n. That cancels out. And we get n equals 36. Okay. So we can also say that, like we can use this formula, right? Notice how we had rearranged into this formula. We could also just jump right ahead and say 360 divided by 10 equals 36. Just making sure that when you're dividing by the degree, you get the number of sides. Okay. All right, that's all for now, and then we'll look at this next week. We'll do some practice problems.